Hello, in this STR8CHEM video, we're going to talk about chemical equilibrium, and to start, let's have a look at what does it mean by dynamic equilibrium. All of the chemical reactions that we have can be classified into two types. We have the non-reversible reactions and also the reversible reaction. One example of the non-reversible reaction is if we have CaCO3 in solid phase, completely converts it into CaO solid and also carbon dioxide gas. So when you look at this chemical reaction over here, it has this arrow over here, signifies that it is a non-reversible reaction. What does it mean by non-reversible? So when CaCO3 solid is decomposed to CaO solids and carbon dioxide gas, it will no longer be able to be reformed, okay? So we do not have a reaction that goes from this direction to that direction over here. You only have reaction going to the forward reaction. Okay, so this is only forward reaction, and we do not have a reverse reaction. So that's why this is a very good example for a non-reversible reaction. So you can say that at your secondary school level, or maybe before you've reached this topic, quite a lot of reactions, if not all of them, will be a non-reversible reaction, okay? So what about the reversible reaction? So reversible reaction would be, one example is this. You have SO2 gas react with oxygen gas, and this time you have that arrow, okay, the reversible arrow, and you're gonna be producing SO3 gas. So the difference between a reversible reaction and non-reversible reaction between these two examples over here is when SO2 and O2 are reacting here, they would be converted into SO3, but in the same time, this SO3 will decompose to reform SO2 and O2 in the reaction. And typically, reversible reaction will achieve equilibrium. And what does it mean by that equilibrium? We're gonna have a look at that graphically later for this example. Whereas, like what I have told just now, this reaction for non-reversible over here, you only have forward reaction going this direction, and you do not get reverse reaction going that direction. Okay, unlike reversible, you have forward and you have reverse reactions taking place at the same time to achieve the equilibrium. Okay, so when you look at this arrow here for topic chemical equilibrium, we're going to use a lot of this arrow. Okay, in fact, all of the reactions that we're going to be using for chemical equilibrium, they are going to be using this reversible arrow over here. Okay, and then phases will be emphasized for this topic. So that is another thing that you need to keep in mind. Reversible reaction will reach a certain kind of equilibrium. Okay, so reversible reactions, for example, this one, they will tend to reach equilibrium. Okay, so that's why you have forward and reverse, forward and reverse reactions that will be occurring at the same time so that you can achieve equilibrium. So reversible reactions will also going to be proceeding forward and also you're gonna have okay, forward and reverse. So when you have this direction over here, okay, forward and reverse direction, you're going to be able to achieve the equilibrium. So when you look at this graph of concentration versus time, this is a very typical equilibrium phenomena that is taking place when you have a reversible reaction like SO2 reacting with O2 to be making SO3. So how do we understand what is going on over here? So over here on this axis, you have your time. Okay, so that is going to be your time. And then over that axis is going to be the concentration. Okay, it's going to be the concentration because all of these gases over here will be having concentrations, and that's how we know they exist. Okay, and also this one. So when you look at SO3, SO3 is your product right there. And at time 0, okay, at time 0 over here, you can see that SO3 is not being produced yet, okay? What you have at time 0 is the concentration for both of the reactants. You have O2, which is that one, and you have SO2, which is that one. So at time equals to 0, when you only gonna start the reaction, you have the concentration for your oxygen. So this is the concentration for the oxygen, as you can see, because it is a reactant. So the concentration will be declining in the beginning, and then it will reach a stable state over here. Okay, same goes to the SO2. So in the beginning, you have a concentration times equals to 0 right here at 0 second. So the concentration of SO2 is right over here, and as time goes by, you can see that the concentration will start to decline. But when you reach this TA at time here, it also going to be reaching some sort of like a stable state. Whereas for the SO3, because SO3 is the product of this reversible reaction, in the beginning you do not have it yet. But as the time is proceeding, you can see that slowly you are making SO3. So that's why you are having this concentration versus time curve over here for SO3. And SO3, same like O2 and SO2, at TA over here, it will start to reach the stable state. So no more concentration going to be added at this state. So it will be constant right there. Same goes to this. It will be constant. Okay, so no matter how long the time you want to keep it up, it will stay constant. Okay, so this one will also gonna stay constant. This one is also gonna be staying constant. So what is going on here, guys? So essentially what's going on over this area there, this is when they have reach equilibrium. The concentration for SO3, concentration for O2, and concentration for SO2. So they have reached the equilibrium right here. So when they are no longer experiencing declining of concentration and increasing of concentration. Okay, so chemical reactions in equilibrium, we have 4 characteristics that you need to know. The first one, the most important one, is chemical reaction in equilibrium will occur only in a closed system. Okay, so means you do not have any kind of interruption from the outside. So the system is very much controlled. Like, for instance, when you see this experiment that is being done to react SO2 and O2, so you can imagine that this SO2 and O2 are put into a jar or vessel, and then you're going to put a lid on it to make sure that the reaction will not going to be contaminated with something else. Okay, so you can imagine that in the beginning you have a vessel, and then you're going to add in SO2 gas, and then you're going to add in O2 gas inside there. Okay, then you have gas O2, then you have gas SO2. This one is at time equals to 0. Okay, 0 second, let's say. All right, and then after a while, what you have now is you're still going to have the SO2. You're still going to have the green one is O2, but this time you start having SO3 in the same vessel, and this one is at T equals to A. Alright, so what does it mean by closed system? Closed system means after you have put all the gas, so you're gonna have the vessel is closed, so you do not have anything else coming in when these two gases are mixing in your vessel to be making SO3, and then they will be reaching equilibrium. So SO3 will exist now together with O2 and SO2. Okay? And then B, the most important thing that you need to include for the characteristics is, like what we have mentioned just now, the rates of forward reaction equals the rates of reverse reaction, or you can imagine that rates reverse equals to rate forward. Okay, so these are the two very important characteristics that you need to remember. At least try to remember these two characteristics for your examinations. Okay, and then the third one, if you're able to remember more, which is going to be better. Try to remember the final equilibrium position for reactants and products is the same. Okay? No matter where is the direction of equilibrium. Okay? And then D over here, the properties remain constant over time. So these are the 4 characteristics of a chemical reactions in equilibrium. So these are the dynamic equilibrium characteristic. Like I said, it's better for you to try to remember A and B. So these 2 are the most important characteristics. But if you're able to remember more, please try to remember C and D as well.